Okay, so hello everyone. Welcome to today's edition of our extremal and probabilistic combinatorics webinar. And as usual, the speaker will talk for an hour or so. Please, if you have any questions, either do ask them in the chat, or you can unmute yourself and ask them directly, or there will be then a possibility to ask them at the end, either in the so official part, or there will be a part where we will switch off the recording. Okay, so know that now everything is being recorded. And so it's my great pleasure to introduce Peter Allen from LSE, and Peter will talk about the regularity lemma and its usage for embedding problems. Peter, please.
Okay, yeah, so I want to talk about some embedding problems. I guess this talk comes from the clouds over Prague. I want to start off by giving some motivation and talking about the size-Ramsey number. Yeah, maybe I should say this talk is kind of a coronavirus mashup. If you look very hard, you may see the difference between my pictures and Julia's. Okay, so size-Ramsey number. I have a graph G, I have a graph F, and I will say G arrows F with a subscript Q if every Q coloring of the edges of G contains a monochromatic F copy. So here is my nice monochromatic purple F within my graph G. Okay, so the Ramsey number of a graph F is the minimum number of vertices of a graph G such that G arrows FQ, and the size-Ramsey number is the same definition but the minimum number of edges instead of vertices. Okay, so these are two fairly classic definitions. And generally, of course, it's hard to find out what is the Ramsey number of a graph. One might hope that the size-Ramsey number is easier. This seems sadly not really to be the case. What can we say? We can say the size-Ramsey number of a graph is certainly at most the Ramsey number choose 2, because the complete graph on this many vertices is by definition Ramsey. Can we do better? So this is what I want to talk about for a moment. Let me start with paths. Okay, so nearly 40 years ago, Beck proved that if we take the n vertex path, its size-Ramsey number is not quadratic in n, as the previous bound would suggest, but actually linear in n. Okay, so Beck gave a bound, and this we can notice for 2 colors. Beck's proof is a very pretty proof. He starts by taking a random graph with capital N vertices. Capital N is chosen sensibly a bit larger than little n, and constant divided by n probability. So this graph has at most 900 n edges, and then Beck explains how to find in any coloring of this random graph a path in the majority color. I don't actually want to talk about how this works, just to make an observation that it doesn't require regularity lemma or other such things. It just uses a simple combinatorial lemma. But the point here is the size-Ramsey result actually comes from a Ramsey result for the random graph. And this is the theme I want to stay on, I think, for this talk. I maybe should say there are graphs where the size-Ramsey number is definitely not the same as the Ramsey number in the random graph, and the square of a path is an example of this. But I'm going to stick to Ramsey results for the random graph. Okay, so the first thing we can look at is what happens if we have more than 2 colors. Okay, so let me first say how to do this badly. This is an illustration of how one kind of traditionally has done embedding results in random graphs. So I want to sketch a proof that the Q color Ramsey number of the path is at most roughly order of n to the 3 halves. So the idea here is, again, we're going to actually prove a Ramsey result for the random graph. So we want to show that a sensibly chosen random graph with about this many edges actually arrows the path. Okay, so how do we do this? We start with our random graph GNP. We impose some conditions which hold almost surely. And then we say, suppose we have this Q color it. Okay, use sparse regularity, which I'll sort of sketch in a moment. What do we get? So the sparse regularity lemma cuts up the pieces of our colored random graph into some bounded number of components. And between these components, we will find regular pairs, sparse regular pairs in one of our Q colors. So in this picture, we've imagined we've found a path going through these 5 clusters where each pair is epsilon dp regular in red. Okay, so what that means is almost the same as the usual dense regularity lemma. If I take a large subset of vertices here, more than the epsilon fraction, and then a large subset of vertices here, again, more than epsilon fraction, then the density between those two subsets of red edges is guaranteed to be close to d times p. Okay, so here d, and it will be throughout the talk, is some constant independent of n bounded away from 0, and 1 over 2q will work. P is the probability of the random graph, so in this example, p will be something like n to the minus 1/2. Okay, now what we want to do is put a long path in red into this colored random graph. We want to use this regular partition. So we put the first vertex in here somewhere, and that somewhere should be sensible, meaning we see lots of red edges going to the next set. Then we put the next vertex somewhere within the neighborhood, sensible, and so on. Okay, if we keep going like this, then we will eventually manage to embed this path of length n into the red edges. In order for this to work, we need to guarantee that when I want to put a vertex in here, I will actually have a choice that has lots of neighbors. And for that, what we want to say is when I put this vertex here, not only do I want to see lots of neighbors here, I also want to see that this pair of sets itself gives me an epsilon prime dp regular pair. So here epsilon prime is some constant a bit bigger than epsilon. Okay, so this probably looks very familiar if you've used regularity at all. The difference to the usual regularity is because this thing is a sparse graph, this set over here on the left side is a very tiny set. We can't just say automatically as a property of regularity, this pair will be regular. We have to ask for that property to hold, which means we need to impose some condition on gamma that says for most choices of a vertex here, in fact, this neighborhood will give us a regular pair. And this property is called regularity inheritance. Okay, now where does this n to the minus 1/2 come from that forces us to only get to n to the 3/2 here? Well, the answer is if I want to see a regular pair here at all, then most vertices on this side had better have degree over to here, at least a large constant. And if p would go below n to the minus 1/2, you can quickly check a typical vertex here would have something like p squared n neighbors over here. That goes to 0, and therefore we can't have a regular pair at all. It's not just that we can't prove this regularity inheritance property, it actually can't be true. Okay, so this sort of strategy of doing embedding using sparse regularity and regularity inheritance has been used quite a lot in the past few years, but it runs into a barrier when we cannot have regularity inheritance because such small pairs cannot be regular. So what I want to do now is explain how to do this theorem, but a bit better. So now I want to say we take some positive mu. I want to show now the Ramsey number is n to the 1 plus mu at most. Okay, so this is going to be kind of a baby case, but this is the strategy I want to talk about for most of the talk. So the idea is again the same. We take our random graph, this time with P being what we need to get this number of edges. So slightly more than 1 over n, polynomially more. Let's suppose that when we apply sparse regularity for convenience, let's say we get t parts. So capital N will be t times little n. So each of these parts has little n vertices. Okay, again, we will find our 5 vertex sets which form regular pairs. Maybe it's convenient to imagine this last vertex set is actually just a duplicate of this first vertex set. So we're going to put in a path, get to here, and then we'll start at the beginning and repeat. Okay, now suppose that we've actually put the first vertex of our path here, and we've made a good choice of this vertex. So I'll try and explain over the course of the talk what exactly that should mean. We want to draw a path going through these vertex sets until we get to this one. And we have some idea already that there is a little set of vertices here which are bad. So as long as we don't choose our path going to one of these vertices, then we will be able to go back to the beginning and say we made a good choice of vertex. Let's keep going.
Peter?
Yep.
I think you are using mouse cursor, but we don't see it.
Ah.
So maybe just click on it. I think if you click on the window, then...
Okay, so I tried clicking. Does anyone see the mouse cursor now?
No.
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 Okay, in that case, I will try to avoid showing the mouse cursor and if necessary, move to a different...
Hi, Peter. I think it's a feature of Zoom, whether you choose you want to share PDF or you want to share the whole screen. And if you say you share PDF, then it's sort of trying to be...
Now we do see your cursor.
Now we see your cursor. Actually.
Okay, then I try telling it to share the whole screen and see if that helps.
I mean, now it works actually. Sorry. It's just
now
fine.
we see it.
Now you see the cursor?
Yes.
Okay, super. Then I hope this continues to work. Yeah, okay. Okay, all good? Right.
Yep.
Okay, super. So what do I mean? That this
the mouse doesn't have a proper Zoom account, so that's the reason, it works always.
That could be. Okay, so what do I mean that this vertex is a good vertex? Well, it should have about dpn neighbors over here, so roughly the expected number. Okay. What I mean that this vertex is a good vertex, well, also each of these neighbors, or at least most of them, should have their own dpn neighbors in the next set. So I'll find about this many 2 paths. And each of those, again, should have lots of neighbors in the next set. So I'll get this many 3 paths. Okay, so this looks like some nice expansion. Now what I want not to happen is this. So I have all the number of 4 paths I should, but somehow they all go to this little bad set. Okay, so this is what I want not to happen. So let's try and explain why it doesn't. Well, if this would happen, I have this many 4 paths, they all go to this little set of size Cn. That means some bad vertex, by averaging, has to get this many 4 paths landing on top of it. And there is a reason that can't happen, hopefully. And this is a result of Spencer talking about rooted extensions. In this particular case, what Spencer's theorem will say is we look in the whole random graph. We look at any 2 vertices, in particular, this start vertex and the one bad vertex that gets this many paths. And Spencer's result will say any 2 vertices are connected by, let's say, not more than twice the expected number of 4 paths. Okay, now this result has some conditions which I'll try and say properly shortly, but one of these conditions I should immediately say is, for this to be true, this expected number has to be growing at least as fast as log n, which means that for this statement to be true, mu actually has to be bigger than a quarter. Okay, so what I'm drawing in the picture is a proof for mu being any number bigger than a quarter. But you can imagine if you wanted mu to be smaller, you would just look at longer paths. So what we want to say is there is a bad vertex that picks up this many paths of length 4, But Spencer says no pair of vertices can be in more than that many paths of length 4, and this should be a contradiction. If we can make C be small enough, so the size of this bad set of vertices, then we will get a contradiction. Okay, the problem with this is what we're trying to fight against is this T here, which is a constant of regularity. So, as I guess people know, normally when you use regularity, the kind of estimate you get for how big is the bad set depends on the epsilon you put into regularity. And then the T that comes out of regularity is some huge constant, much bigger than 1 over epsilon. So a priori, you should imagine that what will happen is you will get C being not all that tiny and T being enormous, and this quantity will end up being very tiny. But the point is we can use something called strengthened regularity, which I'll try and explain later, to say, in fact, we can choose our constant C to be much smaller than T inverse. So this is sort of a magic trick that we're going to use regularity, but our error bounds are going to be tiny compared to the constant that comes out of the regularity. Okay, what does that mean? Assuming we can do this thing of somehow making C be very tiny, then we will say I start looking at my paths growing out of this vertex. Most of them do not go to the bad set. They don't really have to spread out as much as this picture indicates, but what we do know is, say, at most 1% of them can go to the bad set. Otherwise, we would run into this contradiction that too many go to one vertex. So we can choose a path as follows. We start with this vertex that was given to us. Then we choose the next vertex, which isn't in too many paths going to the bad set. Then we choose a next vertex, which isn't in too many paths going to the bad set, and so on. And eventually we choose a vertex which is not bad. Okay, so this is an alternative way of doing a vertex by vertex embedding. We haven't used regularity inheritance. Instead, we've used a result that says broadly things spread out. So this is what one should think of this upper bound on rooted extensions as meaning, and some strengthened regularity trick that says somehow there are very few vertices that can make things go wrong. Okay, so now I want to try and explain how to use this approach in something which is not a baby problem. Before I go on, I should say, actually, the way you should determine the Q-color Ramsey number of a path is to look at Mikhail or Andrzej and Pavel's results, because they already proved that the answer is something like n times q squared log q. The log factor might not be necessary, but the q squared is, and their proofs are kind of much shorter and nicer. Okay, so now I want to go to what our result is. For this, I need to define one more thing, which is partition universality. So this is very much like Ramsey, except that instead of finding one graph monochromatic, I'm going to find a whole family of graphs monochromatic all at the same time. So again, I'll define G arrows family F sub Q to mean I take my graph G, however we Q color the edges, one of the colors, say red, will simultaneously contain everything in this family F as a subgraph. Okay, the families I'm going to be interested in are these two, so G delta n. These are the n vertex graphs with bounded maximum degree at most delta. And the subset of this, G d delta n, so this is n vertex graphs, maximum degree at most delta, and additionally the degeneracy should be at most d. So degeneracy means here is my graph in G d delta n. I've lined the vertices up from right to left. And if I look at any vertex in this order, I should see that at most capital D edges going out to the left. So for this class, I'll generally be thinking of capital D as some small integer and capital delta as some very large integer. Okay, so what's known about partition universality? Let me just quickly mention a nice conjecture from 2000, which is still half open. Suppose I'm not trying to find every graph in G delta n. I just want to find the hardest graph. So I look at the graph in G delta n whose size-Ramsey number is largest. Then Rödl and Semerady conjectured that this grows significantly faster than linear, but significantly slower than quadratic. Now, the lower bound here is still open. We know that there is something superlinear we can write here, but nothing as good as n to the 1 plus epsilon. The upper bound, however, is solved and solved in a rather strong form. So Koyakawa, Rödl, Schacht, and Semerady said nearly 10 years ago, actually, there is a graph which we can Q color, and in one color class, we will find not just our favorite bounded degree graph with n vertices, but every graph with bounded degree and n vertices. And this graph that we are coloring has roughly n to the power 2 minus 1 over delta edges. Okay, so this is bounded away from quadratic in n. What should I say? So this exponent 2 minus 1 over delta, you can't do better than 2 minus 2 over delta here, because just to be universal at all for bounded degree graphs, you need that many edges. So even if you didn't look at coloring the graph at all, you just said, I simply want to find all of these graphs in my big graph with this many edges, then this is how much you need. On the other hand, there is kind of a big gap between the exponent here, 1 over delta, and this 2 minus 2 over delta that is the best lower bound we know. This rather recently was improved by Conlon and Nenadov. They did something a little bit funny, so let me stress. If we look at delta at least 5 and we look at not all of bounded degree graphs, but just the triangle-free ones, then they said we can change this 1 over delta to a 1 over delta minus 1/2. So this is a small improvement, but it's actually a very nice improvement. And the reason for this is when you look at the strategy that Koyakawa, Rödl, Schacht, and Semerady use to get this number, what they do is they use regularity inheritance and they really push it to the limit that you can possibly do. So their strategy works, and at some points it has to consider regular pairs which cannot be made smaller because smaller pairs simply cannot be regular. Okay, so somehow David and Raiko had to find something which is not just regularity inheritance to do this. And I'll try and get to what they did shortly, at least very sketchily. Let me say what we did. So with Yulia, what we can prove is the following. So you give me a number Q of colors, you give me a capital D of degeneracy, and a much larger, you should imagine, capital delta for maximum degree. And you give me a small error mu. Then there is some C such that when I Q color the edges of GNP, where P is slightly bigger than n to the minus 1 over D, then every Q coloring is going to have some color class which is universal for these D-degenerate graphs with linearly many vertices. Okay, so again, this is a universality, partition universality result for the random graph. Why is this one interesting? The reason is this one is optimal in the probability, at least up to this mu. This is easy to see if I generate a random graph with edge probability significantly below n to the minus 1 over d, and I pick any graph with little c times n times capital D edges, then first moment method will tell you in expectation this thing doesn't show up even in the random graph, let alone in Q colorings. Okay, and this of course also gives us a bound on how many edges we need in a partition universal graph for this class, and the bound we get is of course this one. This is also, I think, optimal up to this mu. Again, a counting argument says if you have fewer than n to the 2 minus 1 over d edges, then even without colouring, you cannot be optimal. You cannot be universal for all of these graphs. Okay, so I want to sketch the proof of this result. Maybe now is a good time if anyone has questions about the definitions. Okay, so how does the proof go? So first off, we use a lemma which is implicit in this paper of David and Raiko that I mentioned earlier. So this lemma is kind of horrible. I will try and explain the important bits. The basic idea is we don't need to worry about an embedding where we would care that we don't put two vertices of our graph that we're trying to embed onto one vertex of our host graph. We just need to look for homomorphisms. So how does this lemma actually look? We take a random graph. Okay, it needs to satisfy some pseudo-randomness properties, but the random graph will. We take one of these d-degenerate graphs that we want to embed, and we suppose we can find a big family of homomorphisms from this H into gamma. So psi I minus 1 is a collection of homomorphisms that map the first I minus 1 vertices in the degeneracy order to the random graph. Okay, ignore everything about seed sets because these are just not going to show up. This is some kinds of technical condition that will be satisfied in our proof automatically. The condition we care about is for every homomorphism that puts in the first I minus 1 vertices, we're given a set of vertices, W psi, called the extension set. And what we need is, suppose I take my current homomorphism that puts in the first I minus 1 vertices, and I send the vertex number I to any vertex of this extension set, then I will get something in my psi I, so my one step bigger family of homomorphisms. And this set W psi should be not too small. So what does this say? If I look at the random graph, vertex number I has this many neighbors coming before it. These are the vertices already embedded. And if they've been put to different vertices, then this p to power back neighborhood minus 1 times n, this is how many places I would expect to find in the entire gamma where I should be able to put vertex I. And this condition then says we are getting some constant bounded away from 0 fraction of that as the places we actually could.
Peter, just one thing is that we again cannot see the cursor. So
Okay.
I'm not sure why that's the case.
Okay.
Oh, now we can see. I'm not
okay. Maybe
sure
it only works if I, okay, it can now be seen again.
Yes, so I'm not sure what happens.
Something magic about Zoom. I'll try and wave it up here every so often. Hopefully that will help.
Okay, thank you.
Okay. So the way we should think of this is if I can find lots of homomorphisms from H to gamma, then one of these is going to turn out to be injective. In other words, it will really be the embedding we want. Okay, so I don't want to talk about how to prove this at all, apart from to say that it's a very, very nice proof and you should look at it. But this is really a result of David and Raiko. So what I want to talk about is how are we going to find these homomorphisms. So before I do this, let me quickly say, if we want to use this result with regularity inheritance, which is what David and Raiko did to prove their result, then you will get something that looks like our theorem, except instead of a probability n to the minus 1 over d, you will get a 1 over d plus 2. So this is an observation David and Raiko made. So what we're fighting for is how to avoid regularity and improve the probability. Okay, so how do we do this? Again, I want to use this idea that I showed with the path. We get some weak expansion. Okay, in this path example, we knew that there were lots of paths coming out of a single vertex start, but they couldn't all go to the same place. And we used strengthened regularity to say this same place was small enough. So how does this work here? So let me first state Spencer's theorem properly. So we have a small graph f. So this had better have a constant number of vertices independent of n. We mark some subset of these vertices as the roots and call them capital R. And now what I want to do is I want to say, suppose we put these roots into GNP somewhere, for example here. How many ways are there to embed the rest of f into my random graph? Okay, so here are a couple of ways to do it. I'll notice I only care about the edges not contained among the roots. So I don't really care whether this edge between two roots actually shows up in the random graph. I just care about the edges that involve at least one vertex that's not a root. Okay, so what Spencer's theorem says is if some density conditions are satisfied, then the answer will be whatever choice of pi you make, wherever you put the roots, it will be very close to the expected number. So I don't want to focus too much on the density condition. I'll put it up on the slide for honesty's sake. Here it is. If a graph together with the set of roots satisfies this density condition, and P has this form, which is what we care about, n to the minus 1 over d plus mu, then wherever we put the roots, the number of extensions will be very close to its expected number. Okay, what I care about is this expected number doesn't care where you put the roots. It's just given by some formula depending on f and r and not on the pi that says where the roots go. Again, I don't really care what this formula is. It won't be important for the talk. Okay, so in the example we saw before, f would be a path with 5 vertices and r would be the 2 endpoints of the path. And the density condition would be satisfied for capital D equal to 2 and any mu positive. Okay, so how are we going to do the embedding? So we start with a similar setup as before. Let me draw it. We'll get one difference. So G is the graph we want to embed into. So this is our colored random graph. And let's imagine we've just kept this time the green edges. So the green edges form a clique of clusters in the reduced graph. So each pair of clusters here is sparse regular and dense in color green. Okay, and the graph we want to put in, let's imagine, is this graph F. And we're going to put it in order from left to right. We're going to start by putting the first vertex somewhere sensible. Okay, now somewhere sensible certainly means this vertex where I put this element of F should have lots of neighbors so that I have lots of choices of where to put vertex number I. What do I do when I put in vertex number I? I look far into the future and I say, here is a vertex far in the future. Okay, the picture shows it being kind of 3 steps away, but you should maybe imagine 1,000 steps. And what I say is, when I put this vertex in, I don't want to mess up my ability to put this vertex in at a later stage. What does that mean? Well, this vertex Y, it has 2 back neighbors here. Now, messing up my ability to put in Y means I'm worried that these 2 vertices will be put to some edge here, which has few common neighbors over here. Okay, so this is all I care about. When I put these 2 vertices, I will put them to some edge. I will say this edge is bad if the common neighborhood here is too small. Okay, so that's
Peter, can you activate the cursor so that we, yeah, oh, okay,
yeah.
now it worked. Thank you.
Sorry. Okay, so this thing is a bad pair if the common neighborhood here is too small. And what I want to do is say, when I put I in here, I want to choose a vertex from here that doesn't make it too likely I will be forced to put this pair of vertices to a bad pair here. Okay. So how can I guarantee this? I need to do two things. One of them is something to do with Spencer, which I'll get to later. The other thing I need to do is I need to argue that there are very few bad pairs floating around. So these bad pairs are the equivalent of the bad set of vertices from the path slide. I said I wanted the bad set of vertices, or in this case, the bad set of pairs, is really, really tiny. So how can we do that? Well, first, let's see what we get from regularity. By the way, if anyone has noticed where I changed from Julia's pictures to my pictures, they're free to say. So here we have three parts in a sparse regular partition. Between them, we have in green epsilon dp regular pairs. So let's think epsilon is some very tiny but bounded away from zero number. D we can think of as being 1 over 2q. And for this slide, P you can think of as being basically n to the -1/2. So this is a triangle of regular pairs, and we need to use a theorem of Conlon-Gauss-Samoti and Schacht. And this theorem establishes something called the counting KLR conjecture. And what it says is the counting lemma is true for subgraphs of the random graph where P is optimal. What do I mean by this? Well, suppose I want to count between these two clusters just green edges. Well, this pair of clusters is epsilon dp regular. I don't need to use any theorem to count. Sorry?
Maybe you are using your cursor again?
Does it work again?
Now it's okay.
Okay. Oh, this is really very quick that it hides. Okay. Between these two sets, I want to know how many edges are there in green. So for this, I don't need to use any clever theorem. This is immediate from sparse regularity. The answer is there are this many. So these two sets, let's imagine they have size n. All of these sets have size n. Sparse regularity immediately says the number of edges here is basically d times p times n squared. But what about if I count triangles with one vertex in each set? So for this, I do need to use a clever theorem. And the clever theorem says the answer is what you think it should be if the edge distribution were random. So dp, density between each of these, so dp cubed because I have 3 edges, n cubed because I have 3 vertices. And so this theorem of Conlon-Gauss, Samoti and Schacht says the number of triangles will be very close to what I expect. So this error term epsilon prime is related to the epsilon of regularity. It's a bit bigger. Let me give one more example. Suppose I want to count this graph which is 2 triangles joined along an edge. So the edge is coming here and the 2 vertices left over both go into this set. How many copies of this do I find? Let me say labeled copies. Then it will be again roughly what we expect, which is this formula. Okay, so this is the counting lemma. But what do these 3 formulae tell me? Well, if I apply Cauchy-Schwarz, or if you want to say it that way, the second moment method, what these 3 estimates tell me is for most edges over here, the number of triangles I will find sitting on that edge is roughly what you would expect if the edge distribution were random. Okay, so again, the estimates have got worse. This time I have an epsilon double prime, which is a bit bigger than epsilon prime. Now this sounds actually kind of like what we want. We wanted to say on the previous slide, between 2 clusters, there are not too many edges which are in few triangles. And we're going to be able to say that. There are very few edges, at most this many, which are not in roughly the right number of triangles. In particular, they are not in few triangles. So what this argument establishes is, with sparse regularity, we can argue between any 2 clusters, there are very few at most this many bad pairs. But, okay, if we remember back to the slide with trying to do the strategy in paths, then we kind of saw there, somewhere in the strategy, we lose lots of factors of the regularity constant, the number of parts in our partition. And this is not good because the number t of parts in our partition is huge compared to the epsilon of regularity. This epsilon double prime we get from this argument will be much bigger than 1 over t. And the strategy will not work like this. Okay, we need this inequality to go the other way. Okay, so this is where strengthened regularity comes in. Let me try and explain what this looks like. With strengthened regularity, we still have the partition we had before. This is called the coarse partition. Here are 3 parts in it. We will still find a triangle of green epsilon dp regular pairs. So there nothing has changed. But now we have in addition something called a fine partition. This is just another regularity partition that refines the coarse partition. So that's these little bubbles within the big ones.
And your pointer is gone.
Thank you. Okay. I will try to remember, maybe I need to be shouted at every 30 seconds. What property?
Could be that
Sorry?
it disappears when you change, when you move to the next page.
Ah, okay, then I'll try and remember that. Okay, so what property do we have? First, this fine partition, it is also just a regular partition. Its regularity is some constant epsilon star, and this is much smaller than the number of parts t in the coarse partition. Okay, there is no magic going on here, so the number of parts in the fine partition will be enormous compared to epsilon star. We just get the epsilon star, so the regularity of the fine partition is very good compared to the number of parts in the coarse partition. What is magic is that if we look at pairs of fine parts here, these go between 2 sets that are epsilon dp regular in the coarse partition. Most of these pairs of parts will turn out to be epsilon star dp regular in the fine partition. The point here is, yes, this d is the same both times. Okay, so this is the magic in the strengthened regularity, that we get that somehow these fine pairs tend to line up with the coarse pairs, tend to do the same thing as the coarse pairs. Specifically, if we look between 2 sets, at most an epsilon fraction of the fine pairs will not have this regularity. Okay, so how do we use that? Well, let's just remember from the previous slide, we can still say, suppose I take 3 sets from the fine partition, suppose that all 3 pairs are epsilon star dp regular. The same argument as on the previous slide will say, if I look between these 2 sets, at most this many edges are in this few copies of K3 with the 3rd vertex here. Okay, so this is just repeating the same counting lemma and Cauchy-Schwarz argument from the previous slide. This time we get the epsilon star because these things have that very good regularity. Well, now suppose we could find not just one triangle sitting on this pair of parts, but lots of triangles going to this cluster, and let's say to half of all of the clusters of the fine partition living over here. Then by averaging, we would be able to say, look at edges between this pair of fine parts. At most, an epsilon star fraction of them are in few triangles, overall going to the coarse part. Now, this would be great. This is what we would like, because that's saying there are very few, at most epsilon star fraction of the edges here are bad pairs. This is what we wanted, this epsilon star, this tiny, tiny fraction, much better than 1 over t, of the edges here being bad pairs. The problem is, of course, we are only getting it for 1 pair of fine parts, and what we need it for is for the edges between these 2 coarse parts. So how do we deal with that? Well, of course, we won't generally get that when I look at a pair of fine parts, I see all of these triangles. It might happen that I have a fine part down here where many of the pairs of parts going over here are just not epsilon star dp regular. What do I do about that? Well, there can't be many of those badly behaved parts here because there are not very many fine pairs which are not regular. So I'll just remove any such fine cluster. Okay, so let's suppose I've done that. So I've crossed off a few fine parts from each of these classes. And now let's look. Here I have a pair of parts. These two parts have not been crossed off, so we know that leaving this fine part here, there are lots of epsilon star dp regular parts going out over here, and similarly here. That means between this pair of sets, I will be able to get this argument through. Between this pair of sets, there will be very few bad pairs. So this is good, but of course, some pairs in the fine partition between these two sets still might be bad. There still might be an epsilon fraction of them which are not epsilon star dp regular, and this epsilon is still too big. So the final trick comes in, which is to say, temporarily, let's not look at edges of G between these two pairs. Let's look at all of the edges of gamma, which is the random graph between these two sets. So I've put in more edges here. I've put in all the edges of gamma, not just the ones that happen to be green. But here I still only look at the green edges. Here I still only look at the green edges. What that gains me is now if I look at any pair of parts here, then it will turn out to be epsilon star 1p regular. That means if I look at any pair of parts here, I have something very regular here, and very regular here, and very regular here for most fine pairs here. I have to update the calculations I did previously a little bit, so factors of D disappear from how many edges I get that are badly behaved. But this doesn't matter too much. What I end up with is, if I look between any two of these fine parts over here, which haven't been crossed off, then I will see between these two fine parts, at most, this many edges of gamma are in bad pairs for this cluster. Okay, but of course, the bad edge pair in G is also a bad pair in gamma, so this bound also holds for G. Okay, so what we get eventually out of this is now looking over the entire course parts here, I can say at most an epsilon star fraction of them, okay, will turn out to be bad pairs for this entire course part. Okay, this is what we wanted. So now let me say what we get out of this. Let me completely forget for now about the sparse regularity and strengthened regularity. Yeah, so if you went to sleep, this is the right time to wake up. What we get out of this is, by some tricks for using strengthened regularity, I will find between any two parts, and these parts have size, let's say, n over 2t, between any two of these, I will find at most an epsilon star fraction of the edges here are bad pairs for this third one. Okay, I only showed the argument in one direction, but it was symmetric. It holds between any of these, any pair to the third one. And here my epsilon has been somehow promoted to be much better than the t, which is saying how big are these sets. Okay, so this is what I wanted to get for we have very few bad pairs. Okay, let me quickly say we get a bit more than this and we need it. What we get in general is we will not have 3 clusters, but some big integer number h1 of them. And we won't just be able to talk about edges that extend to a third vertex making a triangle. We will be able to say, show me some bounded size graph F, constant size H0 at most, which is D-degenerate. Let's look at the last vertex here in the degeneracy order. And let's say, suppose that F prime is all the other vertices that come before this last vertex. And I will say an embedding of F prime over here, for example, is bad if the common neighborhood of these three vertices over here is small, so much smaller than you would expect in the random graph. The same argument generalizes fairly easily to say only a very tiny fraction of the F prime copies over here will turn out to be bad. And this works for the probability we're interested in. Okay, so this is kind of the argument I need to make to say there are very few bad F prime copies. Let me sort of quickly sketch how the whole argument then goes. And let me say one more thing. Suppose that this is the graph F that I'm trying to embed, or this is a big constant size part of it. Suppose that over here, I've already embedded these vertices. And so far, I have not done anything stupid, whatever this should mean. And this vertex over here is the vertex that I want to care about not messing up when I embed, say, the next vertex here. How can I be sure that I don't have too much chance of messing up this vertex? What that means is I would like to say this pair of vertices I should not put to a pair of vertices which has a small common neighborhood. So what you would think is, well, I want to apply this strengthened regularity argument with this graph highlighted in green being my F and F prime being just two vertices with no edge between them. Well, the strengthened regularity argument would happily say there are very few pairs of vertices which have a small common neighborhood. Does that mean that when I've put in all of these vertices, I have very little chance of getting stuck on a pair of vertices which in fact does have small common neighborhood? It turns out not, and the reason is if I look at this graph, it has this very dense spot here. If I try and apply Spencer's theorem, what I will find is that the density conditions are not satisfied, and the reason is that there is this very dense spot. It could be that all of the bad pairs, all of the pairs whose common neighborhood is small, happen to be the pairs that live in graphs of this particular shape, and all of the pairs which have common neighborhood that behave themselves nicely happen to be the ones that live in graphs that are not like this. Okay, and it's only the graphs that look particularly like this that I can actually get to if I want to embed this particular large graph. But the way to get around this is to say we can always find some way of expanding this little f that we started with, this just back neighborhood of the vertex, to something a bit bigger until we get to something where the Spencer conditions are satisfied. Okay, but after that, the strategy works more or less as I sketched for paths. More or less. Okay, so let me sort of pre-see the idea. So we do a vertex by vertex embedding. When we want to embed a vertex number I, we look ahead to some far future number y, and we say we don't put I to somewhere which would make it too likely that y gets messed up. And we use Spencer's theorem, we use strengthened regularity to argue that this can be made to work. And then we inductively maintain that we will never cross out too many candidate vertices for our I. Okay, so this is the idea. Maybe let me in the last 1 minute say, something you could ask is, okay, can this strategy be made to work for hypergraphs? Oh, before I say this, I should say, of course, this strategy does not kind of come out of nowhere. 3 years ago, Andreas Nerva and Angelika Steger produced a very nice paper which uses, in a kind of related way, this theorem of Spencer to argue that we only need to do constant distance look ahead. And this is kind of critical. And this inductive counting idea with bad extensions. This comes from some unarchived but not yet published paper of mine with Ewan Davis and Joseph Skolkan. Okay, yeah, so this paper with Ewan and Joseph, this is a paper about hypergraphs, and it sort of made us think, maybe you can also do something like this for hypergraphs. It turns out the answer is you can, so this is a in-progress result of myself with Olaf Parchik and Vincent Fenninger. So this is a resilience statement for tight Hamiltonicity of hypergraphs. So you give me a uniformity at least 3, you give me a small error term gamma, and then the statement is, if you generate the random k-uniform hypergraph, so edges independently with probability p, and p is slightly bigger than 1 over n, then asymptotically almost surely, any subgraph with minimum co-degree a little more than 1/2 of what the random graph had will still have a tight Hamilton cycle. So this theorem is almost optimal in 2 ways. If you try and change the plus gamma here to a minus gamma, then there's a simple construction of graphs which don't have tight Hamilton cycles. And if you try and change the plus gamma here to a minus gamma, or in fact even just to a 0, then the hypergraph itself, the random hypergraph itself, by the first moment method almost surely doesn't contain a tight Hamilton cycle. And the proof strategy here is kind of similar. So again, we use this idea of weak expansion being beaten by a strengthened version of the strong sparse hypergraph regularity lemma. Yeah, if anyone has a snappier name for this, please say, it would be nice. But the idea otherwise is very much in the way that a lot of proofs in resilience in this area go. We show that you can make a connection lemma, you can connect any, whatever good should mean, pair of k-1 tuples in some resilient way. We use some very nice idea of Rich and Montgomery to build an absorbing structure. I think in this case, we called it a reservoir, so I will call it a reservoir. Once you build the reservoir, you find that this hypergraph regularity, the partition has become unbalanced. You don't have much control where the reservoir goes. But this you can compensate for by using a fractional matching and LP duality. You can extend the path, which is your reservoir structure, to something covering most vertices using this weak expansion and strengthened regularity guided by the fractional matching. And then you can use the reservoir in some kind of standard absorbing approach, although the hypergraph version sort of hasn't really been developed so much, to cover up the remaining vertices and complete a cycle. Okay, so I only wanted to say this very quickly, and maybe now is a good time to stop.
Thank you, Peter. Thank you for this talk. Could I ask people to unmute themselves and give Peter a round of applause? Okay, so are there any questions? And let's recall that there will be another opportunity if you are too shy or want to have sort of a more informal question in the unrecorded part.
I have a question.
Mm-hmm.
I was just wondering, would this Q coloring work for size-Ramsey of paths, but in the hypergraph setting?
Yes, it should. Let me immediately say something which is a difficulty. So the difficulty is, okay, this slide will do. So we've used a theorem of Condon-Gower, Samoti and Schacht, this counting lemma. Now, this is an interesting theorem because it comes in a published version and various things which are also true. The published version says this counting lemma is true with P optimal if the graph you want to count is something called strictly two-balanced. Now, actually, for this that I'm talking about, we also need this to be true, not just for strictly two-balanced graphs, but also for graphs which are not necessarily two-balanced. There you won't get the optimal P, but we don't need it. Now, in the paper, they say that this should be true, but calculations are missing, meaning they didn't go back and check a separate paper of Conlon and Gowers where you would need to have various estimates. Okay, so we did something to get around this, which is some kind of cheat trick. And they also say something surely should be true for hypergraphs, but you would first have to decide what you mean by regularity. So in hypergraphs, this is a sort of genuine issue. I think I know what you should mean by regularity, and I think it would be, quote, easy, unquote, to go back to the paper of Conlon and Gowers before this and redo 40 pages of technical estimates for that, and then do this paper over again. But that is a lot of work, and we have not done it. So I think if you ask, say, David, he will probably tell you that the statement is also true for hypergraphs, but there is no actual written proof of it, and that actually will be the main barrier.
Okay, thank you. And I have one more question. And so does this work for grid? Because in the grid, you also have this problem. So the problem is determining size-Ramsey number of the grid. And there's the bound of getting off n cube, which is, and also you had some result, but it seems like this progress you made where you look at the couple of steps further, does that help anyhow for grid?
So for the size-Ramsey number of the grid, so this whole approach cannot do better than whatever you get for the random graph colored, so putting the grid colored into the random graph. Mm-hmm. And there we know something which is, I think, kind of optimal, right? So if any of the authors want to come in and tell me what the result exactly is, Anush, Matthias, I think Dennis, other people. So there is a theorem that says what you can do with coloring specifically the random graph and putting the grid into one color. And this does slightly better than our results. The reason it does slightly better is we have this error term n to the mu in the probability, and they have a polylog factor. But I think this is essentially optimal for the random graph. So our result gives these things, but it's specifically for the grid, probably not optimal.
Mm-hmm. Okay, thank you.
So regarding your first theorem with Julia, would it be at least, would there be an easy guess what the right little c is? So you are embedding, in G and P, and okay, so obviously you can do spanning, but like for when you have 3 colors, there should be an easy guess how big proportion you can do, right?
Yes, my guess is it should probably be essentially the same as if you try and say what proportion of the complete graph can you get. That's already a difficult problem, so we still don't know the answer, and even kind of quite badly we don't know the answer. What our proof gives is spectacularly bad. So for us, this little c will depend on all of q, d, delta, and also on mu in some Wowzer type way.
Okay, thank you.